Today I'd like to show you how to convert a very basic Java for loop into MIPS assembly. So you can see up here we've set up a very standard looking for loop. We've got an integer I which is equal to 0. We've set up a word of that value and we're saying I is less than n, do I++ and print out. Well, we do this actually after we've done this, but that's not so much of a big deal. And this loop prints up everything from 0 to n-1. So let's see how we do that. Well, to start with we need to load our values into registers, so let's load into t0 the value of n, and let's load into t1 value of I. So far so good. This shouldn't be too surprising to anyone, but next we need to do something a little bit different. We need to start up our loop labels. Now remember, these are addresses in memory that tell the program counter where to go to next to start the loop. So I'm going to put one there, and I'm going to set up a condition that this needs to fail, or you could think of it as passing. It's a little bit counterintuitive, but we want to say that I is less than or equal to n. So what I'm going to say is branch if greater than or equal to, I'm going to use the unsigned version, and I think I've gotten it the right way round. I always get this round the wrong way, so we'll see. And I'm going to give this a label to jump to if we meet that condition. So let's put that down here. So I said we want I to be less than or equal to n, and then I've just set up a branch that says greater than or equal to. Now why will this work? Well, it'll work because when this tests to see that I is equal to n, that will mean this condition is failed, and so we branch when we succeed this condition. But succeeding this condition is equal to failing this condition. So this really is I less than or equal to n, at least semantically. Now we'll set up our way to jump to the bottom, but we've not set up a way to jump to the top. So let's put in jump loop. Now this doesn't need a condition, this is an unconditional jump, because once we get down to here it means we've met the criteria up here, so we want to go back around to test again to see if we've met them in the next loop. So now I need to do my printing. Now you'll notice that I didn't put I into A0 despite the fact it's something we're printing. I'm going to show you why I didn't do that later on, but for the moment just bear with me. So since it's not an A0, we need to move it into A0 to print, and we need to load a value into V0. And I'm going to give that 34 because I want to print in hex. And then I need to do a system call. Now that means we've done this printing line here. We've done our I less than n. We've set this up. So now we need to do our increment. And this is quite easy. We just do add immediate. And we're going to give it t1. And we're going to give it the value of 1. So that'll just add on 1 every time we go through the loop. Now if I've set up this correctly, this should work. So let's run this and see what happens and find out if I have put it in the right way around. So let's play. So you can see I am in fact printing out and counting up in increments of 1. However, this is horrendous looking and we wouldn't really want to force this on anyone, so let's figure out a nicer way to do that. Before we do, let's just have a look at what's happening in here. So Mars is quite nice in that when we're doing something like this, it shows us how it steps through the instructions. So this little square that it keeps jumping up around is our loop, at least the assembled code of our loop. And you can also see the values of the registers being updated over here as we go through the loop, which is quite cool. You'll notice I've set the speed down. That's because in Mars there is an issue with memory leaks. So if you've noticed that you've been using Mars for a long time and it's starting to slow down and become unresponsive, that could be because of a memory leak. So if I turn this up to full, it will try and go as quickly as my processor can handle, which means we're much more likely to have a memory leak as I run millions and millions and millions and millions of calculations per second. So I've turned this down. It's also useful just to see us stepping through our code. But let's figure out how to print in a nice way and not this horrendous manner. So to do this, we're going to need to use something that you've not seen before, or at least I won't think you'd have seen before. So what we're going to use is an escape character. Now, you probably haven't seen these before. These will become the bane of your life when you do Python. So what this means is, don't read this as /n. This means that /n has an actual command, and this in this case, /n corresponds to new line. So for example, in Python, because we use Python for a lot of like file manipulation, statistical analysis, you quite often have to give it file paths. But because you're giving it file paths, quite often it will read /something as an escape character, which can be really frustrating. It's not because your code's failed, it's just because that has a different meaning to the compiler. But anyway, we have this now, so we need to do a little bit more work. And this is why I did not store T1 and A0, because we need to load this value into A0 periodically, so it's best to keep our index counting outside of A0 for that reason. So let's load in the word to A0, because I want this to print after I printed my number. And it's going to be new line. And then I'm going to do load immediate to V0. Now, you might think that this should be the same character or the same code as a string, but it's not, it's a character. So let's go to our syscalls. And you can see that 11 is A0 equals character to print. So let's use 11. And then we'll do a syscall. Now hopefully that should mean that our printing's a little less horrendous this time around. So let's assemble this and play. So you can see there we're printing out in nice neat rows. It didn't do that in the first instance because we had previously all that stuff there and we didn't put a new line in to start with. But there you go, so now we're printing out every character. So let's test this at the boundary condition and make sure that it works. That is to say, let's change this so that it meets the condition of FFFF. So if I set this to be 8, we should get a few values printed out and then it should fail this condition and jump to the end. So there you go, we're printing out and we fail when we get past FEE. So this does correspond to less than n. However, one thing I'd like to show you how to do. Now you'll notice that when we finish our code, it says program is finished, it dropped off the bottom, that means the program counter exceeded the size of our memory in the program text section. So it didn't have any commands to complete. But what you can do to exit your program nicely is you can load into V0, value of 10, and then do a syscall. Now 10 corresponds to terminate your program, so this is an elegant way to exit out rather than just letting it drop off the bottom. So let's show you this in practice. So again we get our condition, and then we get program is finished running, not program has dropped off the bottom. If you were in CS 106 in semester 1, that's similar to the halt instruction in Tiny Machine. But yeah, that's everything I wanted to show you today. I hope you found this useful. If you have any questions about anything I've covered here today, please do let me know. Thanks.